Good afternoon. Well, it's a pleasure to be here to celebrate, in some sense, Rami's retirement from a full professor. When I arrived in Bengal University, he was just getting the full professor position, so I should have been here when he's going to emeritus. So congratulations, Rami, for a fruitful professorship. So let's go to business. We were interested in corticohippocampal performance at different pressures, and part of the interest we developed after the first interest was HPNAs. And we were surprised in 2005, we were reading about whales stranding and how these animals may be not compensated in certain respect and get stranded when the use of sonar. And so this developed in further talk with Rami. And then we faced the dichotomy about the high pressure neurological syndrome that human divers experience and terrestrial experiment animals experience when we expose them to high pressure, and the natural adaptation to high pressure by diving mammalians. And here there is an instance of the dive profile of toothed-beaked whales that are good instances for this kind of diving natural behavior. And you can see, if I find, okay, laser, that these animals can dive to close to 1,000 meters, and they stay under the water for around between half an hour to 1 hour, and they do this kind of JoJo diving that some of the people describe here, and they live okay. Just when the sonar is apparently working, they got stranded, but it is puzzling that they are exposed to pressures that human divers in theory cannot tolerate. So either they are very special or there is some explanation for this phenomenon. So here we have some part of the signs that we used to attribute to high pressure neurological syndrome. So I reclassified them and put pretty clear what is HPNAs, like tremor, myoclonus, muscular spasm or convulsions, and so on. And there are other features that we used to put in the same sack. And they're not necessarily pathological. They can be adaptational. We don't know, simply. Easy changes, for instance, or change in evoked potentials, sleep alteration. You are not supposed to sleep under 1,000 meters of seawater. And cognitive symptoms, you are not supposed to see too much or to hear too much at such conditions. So one interesting portion of the behavioral performance of these animals is to be aware of where they are and how to locate where is up and where is down. And so the corticohippocampal areas are now well known to be the region that is able to make use of cortical cells that are called grid cells that tells the individual, in this case rats, where they are with a certainty of 30 centimeters, for instance. So if I move 30 centimeters from my place, I got a grid cell telling me you move 30 centimeters from your original side. And the hippocampus is able to storage maps of known places. So I got a kind of radar on top of a map, and I can tell to myself, where am I? So, you know, high pressure induces a lot of things in a whole animal. So we were interested just on what happens at the pure central nervous system. So we made use of an in vitro system, which is a corticohippocampal slice, where we have the entorhinal cortex, where the grid cells are, and the input to the hippocampus, and here are the maps in the CA1 area. And we were interested in the synapse here that connects the spiny stellate cells of the entorhinal cortex with the dentate gyrus, which is the big entry of the input to the hippocampus. So we stimulated the medial perforant path in the way, and we recorded at the granular cell level the synaptic inputs and then the activity of the cells, and draw conclusion. This, you know, is the pressure chamber. We pressurize, we keep temperature conditions constant, to keep thermodynamic conditions stable. Just pressure is our variable. And regarding the synapse, you have heard about, if we classify the middle perforant pass as a synapse, is moderately saturated, which means it uses, let's say, more than 50% of the resources it has. So it has a relatively high yield. So it's like the climbing fiber in certain respect. So what pressure does to this synapse? Well, it is pretty obvious to you. This is control. This is 500 meters underwater, 51 atmospheres, 5.1 megapascal, and this is 1,000 meters. So you got a clear reduction. And we stimulated at different stimulus intensities to recruit more or less perforant pass fibers. And this is the curve they describe for the amplitude of the synaptic input and for the slope. So pressure, like in other species, pretty reduces synaptic transmission at this level. So what happens when this synapse is dynamically used? So first of all, if you just give two stimuli, like Yoram did with the cerebellum, what you can see is that in control, you got depression for the short interval, very high frequency, and then you have almost nothing in control. This is not facilitation, it's just more or less the same. But if you increase the pressure, well, you see the first event here is reduced, is at 100 atmosphere pressure, but the second event in comparison is increased. So you got an increase in facilitation. So you reduce the first event, but the second event take a gain, probably of the residual synapses that were not released by the first event. Nevertheless, if you stimulate many times, you will not see the same effect. So here you have control. This is control pressure. This is very high pressure, 10 megapascal. And this is the dynamic behavior of the synapse. In control, you see this is normalized to the first event. So you disregard the real size of the synaptic event, and you look at the relationship between the first and the rest of the events. And here you see the facilitation we saw for two events, but then you see that they are depressed almost like in control. So if this synapse was inhibited by pressure, we may reverse it with high calcium. And this, we made a set of experiments to show that. And actually, we increased it. We increased it by about 20-25%, right? And even if we increase calcium further, we couldn't get anything else, which means we were saturating the synapse already at 4 millimolar calcium extracellular, which is the double of the regular concentration in the solution. So you cannot revert. You partially revert the effect of pressure, but you cannot revert it totally. But what happens when you activate this synapse at this condition? So you got here the control that is decaying, but is decaying at a slow or relatively slow rate. When you are at high pressure, you got the first facilitation, and then it decays fast. In the condition of high pressure plus additional calcium, the first event is increased a little bit, but then all the following events are depressed. So it means, in certain respect, we are increasing some events at the expenses of the resources of the rest. Here we compare the increase in the amplitude of a single EPSP at control condition and at high pressure by increasing calcium from 2 to 4 millimolar. So in both cases, we got 20% approximately increase in the EPSP. But if you compare the decay curves, they're exactly the same. What this means? This probably means that this synapse is composed of many sites, and some sites depend probably on a certain calcium channel type that is suppressed. But increasing calcium to the other sites is not able to engage the sites that were eliminated, probably because they're too distant, or because there are sites that depend on a specific calcium channels for release, or because synaptic recycling, the renewal of vesicles into the site is slower than in control, sorry. Okay, next question is, okay, we got a reduction in synaptic transmission, which is completely the opposite of hyperexcitability. We don't understand. So we use a model, and this is what we have. This is the perforant path going into the granular cell, and this is the axon. So we can record the granular cell and to see the spike as a function of the synaptic potential. And you see inhibition is stopping this spiking, and it may play a role in the behavior. So if you look at the single event, you see the synaptic potential, and here you see the population spike, which is the firing of the granular cells in the dentate gyrus. If you look at the curves, and this is control, 100 atmospheres and 50, you see the spike. Actually, the size of the spike doesn't change much. What it changes is the size of the EPSP that is able to elicit a similar spike. So you got hyperexcitability. Yeah, that's true. But you don't have hyperexcitability from a point of view of a granular cell, but you don't have hyperexcitability from a point of view of the system. In the system, you got just the same. This, for me, is kind of compensation, adaptation, or whatsoever. Nevertheless, if you stimulate at high frequency, you may see some increase. And the increase happens when you stimulate at frequencies on top of 25 hertz. So we are showing here a 50 hertz. So if you look at the control, you see the first event doesn't elicit something very serious, but the second event, the one facilitating, is eliciting a huge population spike, which means it's crossing the filter and going to the next area, is crossing the station. And the third also, and the fourth a bit, and so on, and at higher pressure even more, despite that the synaptic potential is smaller. Okay, so here is our explanation for this. So we got a system which is composed of the entorhinal cortex and one kind of input filter that includes this depression. So the input filter, as we can see, probably is not changed because we got the same depression that we used to have. What is probably changed is the transfer function in between the input, that is smaller, and the elicitation of action potential at the granular cell level. So what may happen is that you elicit action potential here, but since they have more synapses here to recruit the recurrent inhibition, when this is stimulated at frequency, the failures at this level and this level are cumulative. So you got 50% change in this synapse, other 50 in this one, another 50 in this one, and inhibition is not enough to cope with the high frequency stimulation. So this we described before, and now what we have found is that we were doing the experiments at the lower range of potassium concentration. And you know, the more you increase the potassium concentration, the more you increase excitability. This is also known for normal conditions. So we got some experiments with what can be the lower level of normality for the potassium concentration, and what is the higher level of normality for the potassium concentration. And what we can see here is that even at control conditions, you got much more firing in the high potassium. But if you compress under these two different conditions, you will have much more fire at high frequency. So this may mean that, of course, animals are exposed to high pressure and they have synaptic depression, and they have a hyperexcitability state for the cells that apparently compensates for this reduction in synaptic transmission. But this is not for all frequencies that the system used to work with. It's just for a reduced frequency range. And if you expose the system to conditions that, in addition, increase a bit excitability, you take it out of control, out of balance. So we can conclude now that from a synaptic point of view, high pressure severely alters excitatory middle perforant path synaptic performance. It depresses single responses, it increases paired pole facilitation, it predominantly preserves synaptic dynamics at frequency. Nevertheless, high pressure also increases corticohippocampal network excitability. During a moderate activity, high pressure increased excitability may compensate for synaptic depression. But during intense activity, high pressure increased excitability may lead to HPNS with cognitive science. Thank you.
Thank you, Adolfo. A nice illustration that we can't always believe exactly what is happening in the synapse. We need to think of the entire network that's operating. Thank you very much.